recording here. We are starting to get as much as new entries in that table of differentiation. That's the second part. So we started with the basic differentiation rules, which ended up giving us the tools to differentiate polynomials, rationals, irrational functions. Then we moved to the trig functions. We worked on the derivative of trig functions. And then there was this stuff somewhere that we learned another rule, differentiation of inverse function. We put it out as a theorem, but that's basically another differentiation rule, like chain rule is, like any other rule we had there. So then we used it to add more entries into our table of differentiation. Inverse trig functions, we all now know how to differentiate those ones. And the last piece that we added at the end of the week before the reading week was the implicit differentiation. It's not a new rule, but it is basically giving you the understanding of how can I deal with these functions that are not defined explicitly. And well, we did some examples there. Now, we are back to the second mission that we started. Add more entries into our differentiation table. And all these rules you have to know by heart. You have to be very fresh when you're using. It's good to start doing the examples when you have all the rules sitting next to you over there on the desk. But just keep in mind that when you're coming to the midterm test and final exam, the expectation is that all that table, all rules, all these knowledge of differentiation is somewhere up here, and you're not allowed to bring any papers, any formula sheet. So we are done with the trig functions, inverse trig functions. Time is for exponential and log functions. That's what we will do today, and that will be the starting point for us. Before I start, is there any questions, any comments in general? Yes, please.
What chapter is it?
Okay, for the midterm, okay, I should have mentioned that. Yes, the big news for us is that the midterm is coming up. It's in 10 days? No, a bit more than, maybe 12 days, something. It's Friday evening, if I'm not wrong, yeah? Is it Friday evening? Yes. Not this Friday, the Friday after. The topics, I checked it twice again. I'm hoping that I'm not making any mistake here. But I'm 99% sure that we will cover all the way to the end of implicit differentiation. To the end of implicit differentiation. So whatever we covered prior to the reading week. Like the topics we are going to do today here is not going to be part of differentiation. Oh, I didn't know that. Okay. I need to hear more questions here. Was that all you needed to know today? Yes, please.
To draw any
When I say calculus from the beginning to the end of the implicit differentiation, it includes actually parts of the review that we did. So transformation, you have to know about those ones. Everything that is there. How many questions will be coming from those review content? Not much, but that's part of the story. Yes?
And short answers?
We will have both multiple choice and short answer questions. Not really the same, but comparable, very close, yes, yes. And just keep in mind that we have regular web assigned quizzes, they're going on. Our second assignment is out and it's due this weekend, yes? This Friday, or yes, end of this week. So make sure that you come back, yes? Don't stay in the reading week. Come back and stay with us here. Okay. Goal is exponential and log function derivative. Okay. We know one of these all exponential function derivatives. This is something that we have been using and you are supposed to know so far. Derivative of e to the power x is e to the power x. Sometimes people actually define the natural exponential function to be the function which has the same rate of change at the point equal to the value of the function. Well, if I go like that, any multiple of exponential function would be the same, would be also sum of an answer for that question. But e to the power x is the one which has value 1 at 0. So e to the power x is the only function whose derivative is equal to itself, and at 0, it is equal to 1. OK, then we have the chain rule of this. Means that if I have e to the power some expression, instead of writing u, I decided go back to my old game that instead of putting u there, I'll put box. Whatever is there, you can differentiate that, and it's e to the power box. But chain rule says that you have to multiply that by the derivative of that inner function, which is box prime. Whatever is up there, you find the derivative of that. Now, the question is, what if I want to find derivative of the other exponential functions? Instead of e to the power x, what is the derivative of 2 to the power x? Or, I don't know, 10 to the power x. These are very simple, similar, but I'll show you how you find that derivative just as basically an example of what we have. The first thing you should know is this small, very useful fact. You can write any exponential, any base exponential function as natural exponential function. Well, obviously, I won't be able to write it as e to the power x. That's not right. B to the power x is not going to, in general, be equal e to the power x. But there is a small thing that I have to add or multiply to the x in the exponential. Can anyone help me out here? Do you know how I can write general base exponential function as e to the power something? Yes?
E to the x? Like e to the...
Oh, OK. So in general, yes, you can write it something times x. But I want very explicit value there. Yes?
X ln b.
Ln b. Yes. So 2 to the power x is the same thing as e to the power ln of 2 as a number times x. Where does this come from? Well, forget that it's b to the power x. You can write any expression you give me, if it has the nice properties, in this case we have those nice properties, you can write box as e to the power ln of box. Can anyone tell me why this is a statement that makes sense and it's true? Why e to the power ln box is equal to box? If that box is positive number, that's basically, yes, please. E and ln are inverse functions, so they cancel each other. Remember, f inverse of x is equal to x. And that is basically written for this specific one. when you have e to the power x and ln x. Now, instead of box, I can plug in this guy here, yes? So b to the power b to the power x is e to the power ln of b to the power x. But remember, ln is a log function, and this power goes out, and you can write it as this. So in summary, you can write b to the power x for any base, any obviously positive base, you can write it as that. How is that going to help me? Because if I know this, now I can try to find the derivative of b to the power x as a case of e to the power, not just x, but a function of x, just a constant ln b times x. Okay? And this tells me how to differentiate that. If you have e to the power box, that would be box prime times e to the power box. Okay. What is derivative of ln b times x? Pardon? Ln b, why do you see that? How do you see that? Sorry.
X is just 1, and you just multiply it by the derivative.
Ln b, thank you. Ln b is a constant. It's a number. Derivative of 2x's.
Sorry, 2.
I need the answer for this. Derivative of 2x's. Derivative of 3x's. Derivative of ln b times x's. Ln b is a constant. It's like 2. It's like 3. So that means that this guy will go away, and I'll just get that constant that I want multiplied to x. How about e to the power ln bx? That's good enough, but we know that whenever we have e to the power ln bx, I can replace it by b to the power x. That's how you find the derivative of general base exponential function. In other words, unlike e to the power x, which has the same derivative, for the general base, we have that part, b to the power x. But I have to multiply it by ln of the base. If it is 2, ln 2. If it is 10, ln 10. Yeah? Before we go on, or maybe I should ask, is there any questions? Any? Yes, please.
Why is it different?
No, didn't I write the last step the same thing? Isn't that same? Yeah? Yeah, yeah. So that's the same. Okay, now I have a question for you. E to the natural exponential function is a special case of general b to the power x. How come for e to the power x then we have two different ways to differentiate? Why these two different formulas, which can work for e to the power x, they don't have any contradiction? They're obviously different formulas, but they don't have any contradiction. Why? Yes, please? If you want, thank you, if you want to use the lower derivative rule for e to the power x, what you need to do is that plug in b equal to e. And then you will get e to the power x. Ln of e is 1. That's how we can get this from this formula. Well, those are equivalent formulas, by the way. And then we have d dx of b to the power box. It's the same thing, ln b to the power box. We have to multiply everything by the box prime. new 4 rules, yes? New 4 entries that, that you have to add to your differentiation table or be able to differentiate those functions, functions of that form. Are we all good? Yeah? You should do some examples. Let's do differentiate the given functions. The first one is f of x is e to the power x squared minus 3x plus 2. The second one is e to the power x squared minus e to the power e over e to the power x plus 2x minus 1. I have 2 more. F of x is 3 cotan x plus 4x minus pi. Another function, cosine x e to the power x minus sine inverse 2 to the power negative 3x plus. All the differentiation rules that you need are all over there. You just need 2 minutes to go through these functions. I am expecting you be able to do at least 3 of these ones. Yes, maybe some of the rules you have to remind yourself or check your notes, but other than checking the derivative of the older functions, everything else is on the board. 2 minutes is yours. Please work on your paper, on your tablet, doing examples. If you're stuck somewhere, please ask the friend sitting next to you. Yes, please. Cosine x e to the power x. Yes, it's cosine x. That's my handwriting. Cosine x
When I get there.
e to the power x. 2 minutes already started, please. Forty seconds left. Yes, it's pi. Yes, minus. Okay, I'll add 10 more seconds before I start doing the derivatives myself. First one, e to the power a function, the derivative, or e to the power box. The derivative is box prime e to the power box. Well, box prime, this is just a polynomial. Derivative of x squared, 2x, minus 3x gives me just 3 e to the power x squared minus 3x plus 2. This one is quotient rule. Yes, I have to differentiate the numerator, the denominator, the rule that we have for the quotient rule. Okay, let's see if we can do it in one step without writing the middle steps. Or I can write the middle steps. Like, okay, this is e to the power x squared, derivative of numerator times denominator minus numerator itself times the derivative of the denominator, e to the power x minus 2x plus 2x minus 1 prime. Sorry, my estimate of how far that will take didn't work again. That's quotient rule. I write that down so that I know what to do next step. Okay, now, derivative of e to the power x squared. That's one of those e to the power box case. So it will be box prime 2x e to the power box. How about derivative of e to the power e? 0. Don't let that e structure, e to the power something, confuse you. Well, if you follow the rules and use that fact, you still be okay. But easier way to understand this, e is a constant, e to the power e is constant. Derivative of any constant is 0. So that would be 0, e to the power x plus 2x minus 1 minus. And well, here I get derivative of e to the power x is e to the power x. Derivative of 2x is 2. Derivative of negative 1 is 0. And then I get e to the power x, 2x minus 1 squared.
That's right.
Any questions, any comments there? Yes, please. Sorry? Louder, I cannot hear.
Simplify for the
We don't know what? Sorry.
simple.
No. We never ask you to simplify when it is about differentiation. Okay, let's do this one. B to the power a function, then the derivative is going to be b to the power x. This is the rule I'm using. It's going to be box prime ln b to the power box. I'm not done because I still have prime here. I have to solve that. Derivative of cotan x is negative cosecant squared. Negative cosecant squared x plus 4 ln 3 to the power cotan x plus 4x minus pi. Okay, this one I'll try to do a bit faster, not writing the first steps there. Well, this is product rule, so let me see. F prime x, the first part is product rule. Derivative of cosine x is negative sine x times the second one plus cosine. Derivative of e to the power x is e to the power x. That's the derivative of this piece here. Now, minus sine inverse. Derivative of sine inverse of x is 1 over root 1 minus x squared. And I trust that you know it. for sine inverse of a function, I have the derivative of that function over root 1 minus that function squared. U prime over root 1 minus u squared. Oh, sorry, I have to put prime here. Now I have to find the derivative of that last piece. I'll just do it here. Derivative of 2 to the power box is box prime negative 3 ln 2 to the power box. You can just put that one in the numerator rather than that. Sorry, this function, you're right. It is actually messy there. Oh my God, it didn't fix anything. Okay, this part is here. The derivative is here, yes? Now, on differentiating sine inverse of box, it will be box prime over root of 1 minus box squared. And here, box prime, I have to evaluate that box prime, yes? 2 to the power box itself is my box here, yes? So I have to differentiate that. Negative 3 is derivative of negative 3x plus 1 times ln 2, because it's 2 to the power something. You always get ln of base there, times b to the power whatever we have. Okay? So what I wanted to do here before I start messing things around is that this part needs to go there. Did it help a little bit? Okay. Yes. Can you ask louder? Okay.
Sorry, like when you
Here, sorry. This is not equality. This is derivative of first part. This is derivative of second part. There are 2 terms there, and the first term gives you 2. And this is product rule, which has derivative of first one times second one plus the first one itself times derivative of second. Are we all good? One more example maybe there? Yeah? Find an equation for the tangent line to the graph where x is negative. For x times 2 to the power, maybe I should do this. Yeah. Remember, to find an equation for the tangent line, can I just quickly, do you need 2 pieces of information? One, the tangent point, where the line is going to be touching the the graph to the slope. The slope of a tangent line is equal to the derivative of function at that given point. Okay? Yes, please.
That last one, sorry. The -3 ln 2, how come that doesn't make it plus u prime over root 1 u minus u squared?
I didn't write that as the whole second part. I said only for the numerator, you need to put that.
Would that make it plus that part over root 1 minus?
You replace the numerator by this.
And you would make it so you have the first part plus, okay, instead of minus, it'd be plus?
See, there is a minus there. This also generates another minus. They will cancel. I'm just saying that this numerator needs to be replaced by that. Yes? Okay. Okay, back to the new example. So you need to find the point of the tangent point and the slope of the tangent line. You need to do a differentiation there. Go ahead, I'll give you 1 minute at least to start doing the differentiation. I'm hoping that you will be able to find the point and find the derivative of the function, and then we go from there. Go ahead, please. Tangent point is the point that x is given. Y value is given by this. So y is f at -1, which is 4 times -1, 2 to the power -1 squared minus 1. And that is, this is 2 to the power 0, which is 1. This part is -4. So the point, or the point that we are trying to see where this tangent line is going to touch the graph has x value -1, y value -4. The slope of tangent line, m, is given by the derivative of the function at that point. So in other words, we have to differentiate it and plug in -1. So here I need to do the differentiation. F prime of general x is given by, this is product rule, yes? Derivative of first one, 4 times 2 to the power x squared minus 1 plus 4 times x, the first one itself, times the derivative of the second one. The second one is following this rule. So b to the power x. Then I will have box prime ln of 2 box prime ln of 2 to the power x squared minus 1, which is the box. Now I have 4 times 2 to the power x squared minus 1 plus derivative of x squared minus 1 is 2x times that, that is 8x squared ln 2 to the power x squared minus 1. Okay. I can factor out ln 2 to the power x squared minus 1 because I'm going to evaluate it, so I want it a bit simpler. So in this case, I'll get 2 to the power x squared minus 1 I factored out. Here's 4 plus 8x squared ln 2. That is the derivative of that function for general x. Now I have to plug in -1 into x there. So this would be 4 plus 8 times -1 squared ln 2 to the power -1 squared minus 1. Well, -1 squared minus 1 is 0 to the power 0. This is 1, so I don't need to be worried about that. I need just to make sure that I have the other values. 4 plus 8 ln 2. So the slope is 4 plus 8 ln 2. And then I can write the equation for the tangent line here. Y minus y1 times equals, 4 plus 8 ln 2 times x minus negative.
That's not my point.
Can you simplify that? Sure, you can simplify, but that is also a good equation for me there. Any questions, any comments? Pardon?
Y minus negative. What is the final right?
That is the equation for the tangent line. When you have a point, when you have a slope, you do y minus y1 equals to m x minus x1. That's, I'm just putting m equal to that value, x1 equal to -1, y1 equal to negative. Yes, please. You have to go louder because they want to talk.
I have to go further to just like solve.
You can simplify this, but the numbers didn't come out very nicely in this exam, so I'll just leave it like that. Yeah. Yes, please. Well, I mean, what is not nice about this number? If I'm accepting from you this formula as equation for tangent line, then there's nothing wrong with this, yes? And you can write. But yes, we try to have. I mean, mathematically, there's nothing bad about that number.
It's still like finding like the y.
I won't guarantee that there won't be numbers a bit, I mean, you know how to work with numbers. Yes? You have to louder, I cannot hear.
Can't we just do y because mx equals b and
Well, good luck. If you go there, then you have to do some more work with that. You can do. You can do whatever method you know. Yes, you can do the other method, y equals to mx plus b, but it will need a bit more work to find b if you're looking for that. Yes. Okay, so I'm done with the exponential functions, but today I am expecting, I'm hoping to do more. In particular, I want to do also log functions, log functions, natural ones, and the general base. The first thing we want to find is this. What is derivative of ln x? I know probably you know it, but for a second, think of what would be a good method for me to calculate derivative of ln x. What would be the good tool to start working on that? Pardon? Well, do you know the derivative of log? This is the simplest derivative of log functions we can find. Yes?
That's the derivative.
You know the answer, it's 1 over x, but how you start creating that answer there? How would you do that?
The box and flip it, and then you take the derivative.
What you're saying, flip it, I think you have the answer for it. If instead of saying flip it, you say, we know the inverse of ln is e to the power x. If we can use the inverse function derivative, that's a way to find the derivative of that. So one method to find derivative of ln x is the inverse function method. There's also another method which is closer to what we did just before the break, the reading break. You can use implicit differentiation also to evaluate that. I'm going to show you that one. So let's say I have this. I want to find y prime. But knowing that, this means x is e to the power y. E to the power y. For a second, forget that I've given you y equals to ln x. Instead, I've given you this equation, and I ask you, and I tell you that y is a function of x, and find y prime. What would you do there? Implicit differentiation, yes? In other words, you start differentiating both sides. Derivative of x is 1. Derivative of e to the power y, when I'm differentiating with respect to x, remember that in the implicit differentiation, we have to use the chain rule formula when we deal with the expressions in y. So it will be y prime, box prime, e to the power box. And then you solve it for y prime. There we go. We found the derivative there, e to the power y. Wait a minute. When we had implicitly defined functions, most of the time we didn't have any opportunity to simplify the y prime. Or in other words, in general, for implicit differentiation, you cannot say that I can get rid of e to the power y. You need to have x and y in your derivative. But in this specific case, we know that y is given explicitly in terms of x. So my expectation, it's not bad expectation if I ask you, can you write 1 over e to the power y in terms of x? And in this case, the answer is yes, because we know e to the power y is that is how we find the derivative of ln x. Derivative of ln x is? Derivative of ln x is? Derivative of ln x is 1 over x. If I want to write the chain rule version of that, I'm writing it in terms of box. It will be box prime times 1 over box. Or in other words, will be box prime over box. How about general log function with the log function with general base b? Well, you can repeat the same story. The only difference is that the derivative of b to the power y would be y prime ln b, b to the power y. So the derivative will be 1 over ln b x. There's also another way to find that. You can use the change of base formula for log functions, and then you can get that. And in general, d dx of log of box base b is box prime over box, but then don't forget to multiply ln b into the denominator. I have some examples for log differentiation of log functions, but we don't have time. You come back on Wednesday. We will do more of those examples. Have a great day, and see you all on Wednesday.